now is section 6.7. And 6.7, we're dealing with formulas and application. And I just want to go over some problems from this section here, particularly working with formulas, and I'll go through some of the application problems. First off, we want to solve variables in formulas, or solve for variables in formulas. So let's say we have something like this. Now let's say we're asked to solve for b. Well, what we're going to do, we want to isolate b. We want to get b by itself. I've got a c over here, so let's move this c. So we can cancel it by subtracting. But what we do to one side, we have to do to the other. Now, we can't do anything with a minus c other than just write a minus c. And this is the best we can do. So that's going to be our answer. Now, for this section, we're basically doing the same thing, theme, but we're going to be doing with some rational functions. So let's take a look. Some rational functions or rational equations. And let's solve for v2. Now, for something like this, I think the easiest approach, again, we want to isolate v2 ultimately, is let's try to get rid of these denominators. That just makes life easier. There's different ways you can do this. You can cross multiply. That'll do it. But let's stick with one of the techniques that we've been working with. So we list our denominators. And they don't really factor. They're just single variables. And then we just need to make the denominators the same, or their factors the same. So this one needs a P1, this one needs V2. So what we're going to get, we can multiply both sides by P1, V2. So if we do that, and then we have some cancellation. Cancel the V2s, cancel the P1s. And so what we're going to be left with, well, it's the same thing we would get if we cross multiplied. P1 times V1 equals P2 times V2. So we want to solve for V2. We want to get it by itself. Now it's multiplied by a P2, so we do the opposite of multiplying, we divide. And since we're dividing the entire side by P2, we'll just have this entire side divided by P2. That's the best we can do. Then we'll cancel over here. This will be P2. And that's going to be our answer. Now let's take a look at another one of these. Let's say we have this. So let's say we're going to solve for r. Now again, we want to get rid of denominators. The easiest way to do that, multiply both sides by capital R plus smaller r. So when we do that, it'll cancel on that right side. So what we'll have left is r plus r times I is equal to e. And we want to get at this r. Now, there's different ways of going about this. And if I look at the answer in the text, they go about it a certain way. And there's a way we can kind of get to the same spot. I'll do it both ways. So one way we can do this, we can divide both sides by I. So we'll get r plus r is e over I. And then subtract capital R. So I'll get R equals E over I minus R. Now, what they actually want us to do is combine these into one term. So we can think of this as divided by 1. And we want to make these into one term. We need common denominators. So we can multiply top and bottom of this term by I. So we'll get R is E over I minus Ri over I. Or we'll get E minus R over I, because they have this common denominator, divided by I. So that's one way of going about this. There is another way. Now let's go back to this step. I'll solve it from the beginning. We got our I equals plus R. Again, multiply both sides by R plus R. Those will cancel. So this is where we sort of branched off. Now we're going to do it a different way. In this case, instead of dividing by I, we can distribute I to get Ri plus little ri is equal to E. And then subtract away the capital Ri. And then finally, divide both sides. Again, you're dividing the entire side. Something you want to remember when doing this. For these types of problems, you're not really dividing just one term. You're dividing the side, which by coincidence has one term. You're dividing that side. and then you get the same answer. So a couple of different ways you can go about this. To looking at how they want the answers in the text, if you want to just play it safe, if you get two separate terms for an answer, try to turn them into the same, into one term using common denominators, and you should be fine. Now, let's say we have something like this. A company is planning to manufacture mountain bikes. There's a fixed monthly cost of $100,000. And it costs $100 to produce each bike. So that's the situation. Now, fixed monthly costs, and then you have each bike costs $100 to produce. What goes into this is when you have fixed costs and variable costs. And just let me double check the definition in the text here. They don't really give one. So fixed costs, what fixed costs are, and this is just from other courses that I've worked in this topic. What they are is that even if you don't produce a single bicycle, you still have this cost. So for example, electricity and rent, that kind of thing. You could argue electricity too. If you're not going to produce bikes, then you maybe you don't turn on the lights. But these are costs that are always there. There. So again, things like rent, insurance. Let's see, anything other than that. If you're paying people by salary, like let's say you've agreed to have a contract, you're going to pay them by salary, and then for a period of time you don't have them come into work, you still have to usually pay their salaries, things like that. Property taxes. But these are pretty standard fixed costs. You know, rent if you're renting a place. Like a warehouse, insurance on your business, or just on the facility, and then property taxes, things like that. So even if you're not producing any bicycles, you'll have to still deal with these things. And per month, you get hit with $100,000. So even if you're not making anything, you still have these fixed costs. The other kind are variable costs. And depending on what you're doing, it could be, say, like repairs. Because if you're not producing anything, you might not need to do repairs. You know, things get broken. Wages. If you're paying people hourly, the more people working, the higher your cost. The fewer people working, the lower your cost, or the shorter hours. Let's see, possibly electricity. I mean, electricity could be a fixed cost if you're going to be switching on the lights on all the time, just to kind of, you know, people do that, for example, to keep intruders away. But if you're only switching the electricity on to manufacture your bikes, or the electricity is going to increase as you're manufacturing your bikes, that could become a variable cost. So things like this. Materials could be a variable cost. If you're not producing bikes, maybe you don't go out and buy any materials. You just don't even bother with it. But once you start producing bikes, you need the bike parts and things like that. So the more bikes you produce, the more materials you need to get. So these could be your variable costs. So what's happening here is your total cost is going to be fixed cost plus variable cost. So the total cost is going to be things like your rent, your insurance, and then plus wages and electricity and materials. And that's going to give you your total cost. So there's a formula that we use in the text for this. And it's going to be this. The total cost C is going to be the fixed plus the cost per unit. Or for us, it'll be per bike. And then X is the number of bikes. So we can treat this, let's see, as your variable cost. So we have our fixed cost, we have our variable cost, and we express the variable cost as the cost per bike times the number of bikes. So that's how we're going to work with this. So that's going to be our approach. Let's see how this works. So part A, write a cost function. So cost function, Cx, is the fixed cost plus the variable. And we're told that the production cost for one bike is $100. So our variable cost will be how much it costs to make a bike. And that could be the electricity that went into this, the wages that went into this, the materials that went into this. Comes out to $100 per bike times the number of bikes. And that gives us the total variable cost. So in this case, it will be Cx equals 100,000 plus little cx. Where again, x is going to be the number of bikes. Little c is the cost per bike. So Cx plus 100x. And so that's going to be your answer. So let's take a look. The next question, they want you to find average cost. Now, the average cost is the total cost divided by the number of bikes. And we denote this as Cx with a bar over the C. A bar over something usually means average. It could Yeah, it's going to be average. That's what it's going to be. I want to say if it sometimes can mean vector. I don't think so. But you're pretty safe, and certainly in this class, calling this average. So this is how we define average cost. We take the total cost divided by the number of bikes. Now, total cost, well, that was 100,000 plus 100x. Now, the number of bikes, well, that's going to be just x. Because we're producing bikes. And if you think about the total cost function, fixed cost plus variable cost, that's the cost per bike times the number of bikes. So the number of bikes is x. So what we're going to do is we'll take this divided by that. And that's going to be our answer. All right. So here's a question. How many bikes does the company need to produce to have an average cost of $300 per bike? So what is the number of bikes needed for an average cost of $300 per bike? Well, what this means is we want this to equal 300. And we're going to have to solve for x. So again, total cost divided by the number of bikes. So now we want this to equal 300. What value of x will let us do it? Well, the easiest way to solve for x, again, is let's get rid of the denominator. Multiply both sides by x. So we get 300x equals 100,000. Subtract 100x from both sides. Now divide by 200. Let's see. And that will give us x is 500 bikes. And that's going to be our answer. Let's see. So let's say we have something like this. So we're now going to look at what we call a motion problem. Now, let's say you've got, let me double check, okay. So the idea of motion is this. Velocity is distance over time. So if you think about miles per hour, that's a speed. And let's say you're going 55 miles per hour. That means you'll go 55 miles in 1 hour. Now, we tend to simplify this, at least with the notation that we use. Instead of saying velocity, we might say rate. And we'll represent rate with the letter R. And then we'll represent distance by D and time by T. Now, we can rearrange this a little bit. We can have R equals D over T, multiply both sides by T. Well, the effect is that the T's will cancel there. And so what we'll get is TR equals D. And then to solve for time, divide by the rate R. So those will cancel. We'll get T equals D over R. Or another way of putting it, time equals distance divided by rate, or time equals distance divided by velocity. But this is the one that we're using in the text. But that's how they get this formula. This is where it comes from. So let's take a look at a question. So let's say we have a passenger train, and it can travel 240 miles in the same amount of time it takes for a freight. If the rate of the freight train is 20 miles per hour slower than the rate of the passenger train, find the average rate of each. And when we talk about rate and velocity, we usually mean average rate. That's what velocity tends to be. When you get into calculus, you can be more specific. But for the most part, for now, we're going to talk about average. All right. So what we've got is a passenger train covers 240 miles in the same time. And this is the same amount of time. I'll check that. I before E except after R. Just kidding. Anyway, freight train. It's usually I before E except after C. Special case there. So we've got that, and the freight train is 20 miles per hour slower. So what do we want to figure out? Well, let's use that technique for solving problems. Now, what they want us to find are what are the rates of travel or the speeds for each of these trains. So that's the key things. That's going to tell us what we're looking for. So let's go through I'm going to go through the 4-step process. Let's do that. So number one, what do we know? Well, we know that the passenger train is 240 miles per hour. Oh, sorry, no, passenger train, we don't know the rate. Passenger, it covers 240 miles. The freight covers 160 miles. And this is in the same amount of time. So we've got this. We also know that the freight train is 20 miles per hour slower. So we do know something about rates. So what do we not know? Now, you can argue, of course, that clearly what we don't know are the rates of travel for the passenger and freight trains. We also don't know the time, to be fair. We don't know the time. And this might not be as important later, but we do know something about it. It's not totally a mystery. We do know that they travel these distances in the same amount of time. We do know the trains travel the two distances in this time. So I know a little something about it. The big mystery, though, is the rate of the passenger train. That we definitely know nothing about. We know a little something about the freight train. There we go. It's not terribly mysterious. We do know this. It's 20 mph slower than the passenger train. So we don't know the time that they're actually traveling. We don't know the rates of the trains. Now, here's the thing. We need to come up with something in step 2 that's going to be a variable, the unknown we're going to solve for. Do we solve for the time, the passenger train rate, or the freight train rate? Well, we want to look for an unknown that if we find it, maybe the other unknowns become solved. And this is my argument. If we knew the rate of the passenger train, it's very easy to get the rate of the freight train. Whatever the passenger train is traveling at, subtract 20, and we've got the rate of the freight train. So if we find this, we'll find this. Finally, what about time? Well, time is distance divided by rate. We know the passenger train travels 240, so we have this. And if we find the rate of the passenger train, we can put that in for R. So 240 divided by the rate here, if we find it, will give us the time. So here's the thing. If we find the rate of the passenger train, we'll easily find the rate of the freight train, and we'll find out how long these two trains were traveling for. So the thing, the domino that sets everything else in motion, so to speak, the rate of the passenger train. We find that, we're going to find everything else. So let's solve for that. So for step 2, X is the passenger rate. Now that means we're going to get this. Time, which is D over R, well, the time traveled would become 240 over X. If we find X, we'll be able to find T. Also, we'll be able to find the freight rate. That'll be X minus 20. So if we do need to find the time, it's in terms of the passenger rate. And the freight rate is X over 20. So we got to come up with an equation. How do we construct an equation? Well, here's my argument. The trains travel for the same amount of time. Now, in that amount of time, the passenger train, which is going faster, will cover 240 miles per hour. The freight train, which is going slower, only gets 160, but they're still traveling for the same amount of time. So that's the key clue. So let's go back to this. this time will be the same for both trains. So for the passenger train, it'll be 240 divided by x. You don't know the rate for the passenger train, so we're going to just call it x. So passenger. Now for the freight, same time, but only travels 160. But what's the rate? Well, we're told that the rate is 20 miles slower than the passenger train's rate, or that x minus 20. So these are the same time, so we can equate these two using time. So 240 over x equals time, which is going to be 160 over x minus 20. And this is only true because we're told that they travel for the same amount of time, just one travels slower than the other, and so the faster one covers more distance than the slower one. So we can drop this t out. And we'll get 240 over x is 160 over x minus 20. That's the equation we're going to solve. So to solve this equation, there's different ways you could go about it. You could, again, and I'd recommend this, cross multiplication. Great way to go. Just for consistency, I'm going to stick with the technique we've been using with the multiplying through by a common denominator. So we have our denominators. This factors to x. X minus 20. That just factors to x minus 20. And then what do they need? Well, this one needs x minus 20. This one needs an x. So we'll multiply by x times x minus 20. So we cancel. And what we're going to be left with we distribute the 240. Subtract 160. So we'll get 80x equals 4,800. Divide by 80. And we get x is 60, and this is 60 miles per hour. Fine, now that's the speed for X. That's the passenger train. For the freight train, we need X minus 20. Or 40 miles per hour. And that's it. So any questions, let me know. I'll do another section on these story problems because there's a couple other types we need to go over. Another kind of motion problem and also work. But let me know if you have any questions and hope to hear from you soon.